We're gonna be solving section 2.3, which you will be tested on in the science finals. And it's the last course practice quiz that you have to do. So 2.3 matter. So let's start. Here. What are two changes that take place when heat is released? Now, guys, we have two scenarios of what happens during heat. One is when heat is released. And two, it's when heat is absorbed. Okay? Let's see what happens in each case. When you're releasing something, you're letting go of it. You're taking it out. So taking out, we're gonna write here. So now, merge these two together. When the heat is being taken out, that means what's happening to the object? It's cooling down. Okay? So when heat is taken out, the object is cooling down. Now let's see the second scenario. It's when heat is absorbed. When you absorb something, you take it in. So taking or take in. Okay? Just like how plants, they take in sunlight, they absorb the sunlight, right? So let's see. When heat is taken into something, this something is getting heated up. So heating up. Okay? So once again, when heat is being released or taken out, so heat taken out, it's cooling down. And when heat is absorbed means taken in, right? So when heat is taken in, the object heats up. Okay? Let's see. Here, what do they want? They want when heat is released. And here we know that when heat is released, the object cools down. Let's see. Boiling. Now here we're going to go through each one. Boiling is when a liquid changes to a gas, okay? When a liquid changes to a gas, you have to increase the heat, right? And basically, when you're increasing the heat, you're absorbing it. Are you releasing it? No. Because once again, when heat is released, the object is cooling down. Cooling down. Let's see. Sublimation is when a solid changes directly to a gas. Now, sublimation and deposition, guys, we're going to be discussing them later on in the quiz. For now, I'm just going through the key points. Sublimation is when solid changes into a gas without forming a liquid, right? So, solid all the way to gas, you need to heat it up, right? So, obviously, when you're heating something up, you're absorbing the energy. So, wrong. Condensation is when a gas changes into a liquid. And if you don't know whether this is heat up or heat down, let's compare it. Here, when liquid to gas, the heat is up. So from gas to liquid, here it's vice versa. The heat is going to decrease. And cooling down, the heat is decreasing. So is this correct? It is. Why? Because for something to turn from a gas to a liquid, you really need to cool it down, right? And cooling down is when heat is released. Okay? Let's see next. Freezing. To freeze something, it changes from a liquid to a solid. And here, this one's really easy. For example, if you put water into a freezer, which is obviously cold, the water cools down and freezes. So obviously, without even thinking about it, the heat is being released. Melting, it's the opposite, from solid to liquid. Okay? So let's see here. You have from liquid to solid, the heat is going down, right? So from solid to liquid, the heat is going up. So is it releasing the heat? No. So what are our correct answers? Condensation and freezing. So the key points. When heat is released, the object cools down. And which two changes in state cause for a substance to cool? Condensation and freezing. So condensation and freezing. Let's see here. Which two statements are true about a substance being cooled? Now, from the previous question, when a substance is being cooled, the heat is being released. So, what happens to the particles? Okay, now the particles move in different ways. One is when something is cooling, in which the heat is being released, and one is heating, when the heat is absorbed. Let's see how particles react. Now, here, you need to know this. When something is cooling, the particles move slower. Move slower. Okay? So, you need to know this. When something is cooling down, the particles move slower. Let me give you guys an example. Here you have some liquid water, let's say. Okay? And let's say here you have liquid particles. They're moving freely. They're moving faster. But then when it's cooling down, so cools down, what do you expect to happen? It's going to turn into ice, right? And ice particles, ice which is a solid, its particles are tightly packed together, right? Like this. Okay? So how did the particles go from this to this? Obviously, they moved slower so that the particles had the time to stick to each other. Okay? So when something is being cooled, the particles move slower. What else happens? When something moves slower, it loses energy. Energy. I'm just gonna write it here, next to it. Loses energy. Now, why? Let's say you are running, okay? You're running really fast. But then, all of this sudden, you're just slowing down. Why do you think you slowed down? Because you began to lose your energy. So they relate. Right? So when the particles move slower, the particles lose energy. And when particles lose energy, the particles move slower. So they relate. Okay? What else happens during cooling? The particles get closer. Now you might be like, why do they get closer? How? Here, in the liquid particles, they were free to move, right? But then in the solid, they're really tightly packed. Okay? Let's say in this scenario, you have a group of people in this room. Okay? So, multiple people in this room, let's say. You have those two people. They have their own space to move, let's say. Now they're placed in the same room, but they're squeezed to each other. Like they're really squeezed, right? You noticed here, they're far apart. Here, they're closer. So what do you think happened? The two people, they moved a bit closer to each other, right? So from something to be free to being, that goes from being free to being packed, they get closer. Now heating, as long as you know cooling, heating is the exact opposite. Heating, particles move slower. So what do you expect here? Particles move faster, right? Why? Because if something that's cooling loses energy, something that's heating gains energy, right? They also relate. Okay, for example, when you're running and then all of a sudden you just get like so much energy from whatever it is, water, nutrients, whatever, you're gonna begin to move faster, right? So they relate. Particles move faster when they gain energy, and when particles gain energy, they're gonna move faster. And here, in cooling, the particles get closer, so in heating, the particles get farther away. So they get farther. Here's another example. Let's say here you're going from an ice cube to liquid water. Let's say, and here it's heating. So heat. In ice, the particles, they're really tightly packed, right? So here the particles are packed. So it goes from being packed to being more free. If you're not here, free. So when something goes from like having pressure, it's so tightly packed, to just being more free, more away from each other. I just said it, more away from each other. So the particles, they are getting farther or away. Okay? Take a look and I'm going to start answering the question. So which two statements are true about the particles being cooled? So right here now, we're focusing in the cooling area. Okay, here is for the question. The particles, they move slower. Correct. Wow, we just wrote it here. The particles, they move slower when they're being cooled, right? Now, if you guys like want this as an example, let's say like you're sitting down on like a really cold day, you would like just wrap yourself up to get warmer. You wouldn't like really do that many activities, right? So basically you have less movement. So will the particles. They're going to move slower, right? They get closer to each other. Remember here when we discussed the water particles, they're free until they turn into packed particles. What do you think happened? Just like the people, they moved closer. Change in size, it doesn't relate. So no. What did we say? When something moves faster, it's getting heated, right? So the particles, they move faster, right? In heating, not in cooling. So don't confuse them. Either way, here we already ticked slower. So faster here for sure wrong. And let's see the last option. They move away from each other. What did we say? When something moves away from each other, it's getting heated. Remember here? When we have a solid and let's say it melts to a liquid, the particles turn from being packed to being more free. So when like something is tightly packed and then just more freedom to move, they're moving away from each other. But this is for heating. So wrong. So the two correct answers is that when the substance cools, the particles move slower and the particles get closer to each other. Okay? So let's see, they move slower and they get closer to each other. Question 3 says, which two statements are true about the particles of a melting substance? Let's see. When a substance is melting, it changes from a solid to a liquid. So, what do you expect? If something changes from a solid to liquid, obviously it's going to heat up. And let me circle that because it's important. Heats up. So, when the particles heat up, what did we say happens? Heats up. What happens? The first thing that happens, we know that the particles move faster. Guys, you need to know this like how you know your name, okay? So when you see heats up, directly in your mind, particles move faster. Okay? Cools down, directly, particles move slower. Okay? Now, when something moves faster, it's going to gain energy. So the particles gain energy. By the way, guys, I'm just recapping this because I already wrote it down in the previous question. So they gain energy, right? And we said here, for example, when we have solid ice and then it changes to liquid water, right? I'm just gonna use this for the particles. Once again, what happens to the particles? They're moving farther away. Notice here the difference. Here they're so close, they can't even move. Here they're free. So the particles move away from each other. I'm just gonna write move away. Okay? So once again, when something heats up, the particles move away from each other and the particles move faster. And for something to move faster, it needs to gain energy. So now let's see. They become motionless. This is wrong because even solid particles vibrate. Nothing is motionless. They move slower. Wrong, because here we said that the particles move faster. For moving slower, this is cooling, right? But when something is melting, it's heating up. Okay? So this is wrong. They move away from each other. What did we write here? They move away. Oh. Here, they move away, right? So this is correct. They gain energy. Once again, for a particle to move faster, it needs to gain energy. So this is also correct. They get closer to each other. What did we say getting closer is for cooling? Okay? Once again, here, the same example I keep giving you guys. Here, we have from liquid to solid ice. The particles turn from being free to being tightly packed. Right? So obviously what happened? They move closer. But this is for cooling. Right? What do they want here? Here they want heat. So what are the two correct options when something is being heated? When they say they mean the particles, okay? So the particles move away, yes. And the particles gain energy, yes. Okay? So they move away and they gain energy. Let's see question 4. A student places a bowl containing several ice cubes on a lit stove. He then places a thermometer in the bowl and measures the temperature inside the bowl for 2 hours. The graph below shows the temperature versus time graph of the recorded measurement. Now guys, this question is actually easy. So let's do it step by step together. A student places a bowl containing several ice cubes. Before, we need to know the substance. When something is ice, it's basically frozen water. Oh, here. Frozen water. Okay? So now let's see. What is the information we know for water? About water? It boils. Boiling point, we know, is 100 degrees Celsius. And the melting and freezing point, here, points, are 0 degrees Celsius. Okay? So let's see this table and record it step by step. Here we have B and C. They're both at the 0 degrees, okay? But here you notice that the temperature it's the same, but time is progressing. So what do you think is happening? It's melting, right? I'm just gonna write it down here, melting. So first I'm gonna state the action and then the points. So don't worry. B is exactly at 0. It starts at 0. And what starts at 0 degrees Celsius? Melting first. So this is the melting point. If you guys still don't understand, it's okay. B starts at 0 degrees, okay? And what starts at 0 degrees when time is progressing? Melting, okay? So B alone, guys, is the melting point. Yani if they ask you what's the melting point, the melting point, this would be B. Okay? So now let's see. From B to C, okay? So here we reached B. B is the melting point, we said. So B and after, it's gonna be melting, okay? Understand? So B to C, it's melting, and B is the melting point, sorry. But now here, we have A. What did we say? 0 degrees is also the freezing point. So here, let's rewind the time. Yani B, it's also the freezing point, right? So freezing point, guys, it's also B, right? So now B to A. A is now below 0 degrees. So خلاص, A is ice. But B to A, it's freezing. Oh, here. So basically here, they're just checking your understanding. What happens at 0 degrees? Substance melts and freezes. So now let's see. Also here you can use this graph. 0 degrees. After that, it's melting. Before 0, 0 and before, it's freezing. This can actually be helpful for you. So here, 0 and after, it's melting. And 0 and before, it's freezing. Or already frozen, okay? So here, 0 and after it, it's melting. And 0 and before it, it's freezing. But here, we said that A is ice. So what do you expect C to be? C would be water, right? Guys, in this question, what's confusing is that there are actions, points, and states. So B is the melting point. Actually, I'm just gonna do it again. Just take a quick look. I'm gonna redo it for extra explanation. So we have point B, C, and A. B here is the freezing and melting point, right? Points. So here we're gonna have the point. So now we're gonna do the action. B to C, it's melting. This is the action. And B to A, it's freezing. This is like a summary about these 3 points. Okay, so B is the freezing and melting point. B to C is melting and B to A is freezing. But now C alone is just water and A alone is just ice. I'm going to keep this on the screen for now while I explain C to D if you want to just take a look at it. It's a summary. Now let's start from C all the way to D. So from C to D, what do you expect all this to be? Look here. The temperature, it's increasing, right? So, what do you expect here? Let's say, for example, here it would be 20 degrees. Let's say here it's 60 degrees as an example, okay? But here it just keeps going, 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 going. Okay? Did we reach the boiling point yet? No. So C to D, what do you expect there to be? Liquid water only. So liquid water only. Okay? Only until D will something start boiling. So D here, which is 100 degrees Celsius, is the boiling, let me just write it more clearly, is the boiling point. Okay, so let's stop here and revise what we did. So now you guys know A, B, and C because of this here. Okay? So starting C. What did we say is C is water? And then C all the way to D, it's only liquid water until it starts to boil at D. Why? It is because it's the boiling point. Guys, when something boils, it changes from a liquid to gas, right? So basically, D is still a liquid even though it's boiling still, right? So this full time lapse, it's only liquid water. Don't let it confuse you, okay? So I'm just gonna remove this right now. So once again, C, halas, it's when the ice melted, so it's water. And C all the way to D, it's also water. Until D here, we said it's the boiling point. But then when something starts to boil, it's still a liquid. After some time, will it change into a gas? So what you need to know, C to D is only water, basically. Okay? So now here, we're gonna have point D. D here we said is the boiling point. So D to E, actually I'm gonna use a different thing. So here we have D, E, and F. I'm gonna do the same thing as I did for A, B, C. So D here, we said it's the boiling point, which is 100 degrees, right? So here, D to E, what do you think is happening? What's the action? Boiling. So now here, E to F. So here it's boiling. Now at E, it stops boiling. So what do you expect E to be? E would be a gas. And what gas? Water vapor. So no matter now, whether it's now 200 degrees, 300 degrees, after E, it's only water vapor. So just like ABC, here's a recap for it. D is the boiling point. D to E, the water is boiling. And E to F, it's only water vapor. Okay? So just take a look at it. And let's answer the questions. Let's see. Okay. Only water vapor exists. Now, you guys, remember we did here D, E, F. We said D to E, it was boiling, right? And E, it stopped boiling. Remember, I said E to F, it's only water vapor. Whether it's 200 degrees, 300 degrees, خلاص, it stopped boiling here. Here, exactly. And after this, it's water vapor. Because it's still 100 degrees. After that, will it, done. Okay? So according to what I drew here, E to F is only water vapor. So here, E, F. Now, just as a repetition again, D to E, it's boiling. Here, it stops. And then when it stops boiling, it's gonna be water vapor. I'm just gonna write, no, it's fine. I'm just gonna write water vapor. Okay? So if E is water vapor, is there any stage after it? Can a gas just change into something other than gas? No. So here, water vapor, infinitely, okay? So if you have here point, let's say you have here point G, H, I, all of this, it's still water vapor, okay? So when you only want water vapor, it's between E and F. Now, only solid ice exists. Now, remember when I did B to A, right? B is 0 degrees, which is the melting point. Okay? And when something melts, it changes from a solid, which is ice in this case, to a liquid. So when something starts melting, it starts as ice. It's not magically water in the beginning, right? So when it's still ice, it's B to A. So B, A. By the way, guys, this question is a bit difficult, but with more practice, it's gonna be easy. Here, only liquid water exists. Now, here, this was the main part. Remember here, I did this full thing, and I said that C to D is only liquid. Remember? So, where is it only liquid? C to D. Now, both liquid water and water vapor exist. So, let me see. The answer is D to E. Now, guys, why? Here, let me zoom in first. Here, you have D, which is 100 degrees. So, 100 degrees, it's first a liquid, and then it turns into a gas. And then remember when I said that E, it's water vapor. خلاص, it stopped boiling. Just gonna write water vapor. Right? I said E, and after E, it's only water vapor. But which one has both D, because it starts as a liquid, and E because it finished boiling and it's water vapor. Okay? So why D? It started boiling as liquid water, and E because it finished boiling as water vapor. Let's see. Beyond point E, the substance remains in the gas state. Because remember here, I said anything after E, it's only water vapor. I'm just gonna write water like this. Remember here I said whether there's point G, H, I, whatever points, it's only gonna be water vapor. But what's the difference? The particles are moving rapidly. Why, guys? Let's discuss this. We didn't do it yet. Here, watch this carefully. The time, it's increasing, and the temperature, it's also increasing, right? Then we said that when the temperature or heat increases, what happens to the particles? The particles move faster. right? So here the heat is increasing and the time is also increasing. Oh, it's fine. So the particles, they're gonna move faster. This is why they're moving rapidly with the increase of the temperature. Okay? And by the way, the question we just did, it's probably just the hardest compared to the others. Now here, it's really, really easy. Melting. What's melting? It's when solid changes to a liquid. So which one says that? Solid to liquid. So this is for melting. Now for condensation. Condensation, gas to liquid, right? Gas cools down to become liquid. Which one says gas to liquid? A or 1. Gas to liquid. Okay? So now, next is vaporization. Vaporization, which is a form of evaporation, is when a liquid changes to gas. Right? Vaporization, by the way, guys, it has boiling, and evaporation. Evaporation. If they ask you for the difference between them, this is how I like to think about it. For example, which one happens at a specific temperature? Boiling. How do I think of it? I say boiling point. A point is really specific. So specific temperature. Right? So the boiling point, a point is a specific temperature. Right? And evaporation is just when it leaves the surface, whatever. But the important thing, specific temperature, it's boiling. We're gonna discuss it more in other questions. But here, the important thing, liquid to gas, liquid to gas. Now the last one, the easiest one, freezing. Freezing, it's when it changes from a liquid, yani example water, to a solid, which is ice. So which one says liquid to solid? This one here. So here, it's really easy. They're just testing you on the changes in state. And this is really, really important. Any change in state is a physical change, okay? Because they always ask you this. Trust me, they're gonna ask you this at some point for sure. So any change in state, sublimation, deposition, melting, condensation, freezing, evaporation, these are all physical changes. Okay? So now let's just match them. Melting. Oh, melting is solid to liquid. Condensation, gas to liquid. Vaporization, liquid to gas. And freezing is liquid to solid. Okay? Here. The process in which a gas becomes a liquid by increasing the pressure. Now guys, here we're gonna be discussing gas liquefaction, or you might also see it as gas liquefaction. Okay? They're the same thing. So basically, gas liquefaction is when you change a gas to a liquid by increasing the pressure. Basically, how does it work? Those gases, they're going to be placed inside these cylinders. But actually, they should be a bit smaller, I think. Like these types of cylinders. Where the gas particles, they don't have that much space to move. So this, when there's not that much space to move, I'm going to use right here. Those particles are going to start to attract to each other. Right? So apparently, eventually, these gas particles, they're going to keep getting closer to each other, closer and closer, until over time, when you increase the pressure, what are you gonna have inside? I'm gonna use blue for this. You're gonna have, oh my goodness, liquid water. Did you cool it? No, you didn't. In gas liquefaction, you change it from a gas to liquid by increasing the pressure. Because what happens when you increase the pressure? It favors, what does it favor? Attraction. Okay? So these gas particles, they're gonna come together to make a liquid particle, or many liquid particles. Okay? So gas to liquid, increasing pressure, gas liquefaction. Here. Now, here. The process in which a gas becomes a solid without forming a liquid. Now, this is when I'm going to be discussing sublimation and deposition. Now, guys, in sublimation, how I would think about it, as for sublimation, as for solid, solid, and it skips liquid, so it doesn't form a liquid in between. See guys here, sublimation, solid skips liquid. So when it skips liquid, what is it gonna turn into? A gas. Now deposition is just the opposite. So what do you expect? Gas skips liquid and changes to solid. So guys, it's really easy. But I want you to focus on sublimation because deposition is the exact opposite. But sublimation, it just has more like keys. Solid, sublimation, skips. Okay? Because if you know one, the other is the exact opposite. So let's see here. The process in which a gas becomes a solid. What did we write here? Gas to solid is what? Deposition. But when it says solid to gas, as for solid, as for what? Sublimation. But here, what do they want? They want from a gas become solid. So what is it gonna happen? Deposition. Here, Rami carried out an investigation to find out the boiling point of an unknown liquid. His results are shown in the table below. Now guys, this is actually really easy. First, we need to find the liquid. Do we know what it is? No. Let's see. The boiling point of a liquid is... Now guys, how do you know the boiling point? You might be asking yourself that. The boiling point is when you see the same number 2 or more times. Or actually, 2 or more times. Because what does it mean? It means it can't heat up more than this. Khalas, it already became a gas, right? So let's see here. Which substance, which temperature appeared more? Time, 0 minutes, 20 degrees. 1 minute, 35 degrees. And so on until you reach this. 4 minutes, 5 minutes, 6 minutes, 2 full minutes, and it's still 100 degrees. Right? So here you spend 2 minutes and still 100 degrees, 100 degrees, and 100 degrees. So what do you expect the boiling point to be? 100 degrees appeared literally 3 times. The question is making it obvious for you. So what will it be? What's the boiling point, guys? The boiling point is 100 degrees. So basically just check towards the end which number appeared 2 or more times. Just use this method and you can find the boiling point. Okay? And if, for example, they asked you, what is this unknown substance? What boils at 100 degrees? Water. Okay? So the boiling point here is 100 degrees. Question 8 says, the illustration below shows the different processes involved in changing states of matter. Drag and drop the processes from the box below. Now guys, this question is actually really easy. Let's see here. When a gas changes to a liquid, what do you expect to happen? The gas will condense. So this is condensing. Condensing. Here. So now, from a liquid to solid. So it turns from liquid water, let's say, liquid water to solid ice, let's say. What do you think happened? The object was freezing. This is actually like, it's okay. It's just testing you in the changes of state. Now here. Actually, just let me do this here. I'm gonna use blue here. You know why? Here, freezing. Why? Because those two, the object, it's cooling down. So here, cools down, right? Because freezing and condensation, the object cools down, right? And so is here. Just gonna write C, D. And here, from a solid to a liquid. Now here, just ask yourself the exact opposite. What's the opposite of freezing? Melting. And what's the opposite of condensation? Boiling or evaporation. Oh, boing. Here. So, liquid to gas, it evaporates or boils. So here, your heats up. So, you can take a look at it before I put the answers. So here, gas to liquid, condensation, liquid to solid, freezing. So solid to liquid, opposite of freezing is melting, and liquid to gas, boiling. State for each process, its corresponding change of state and whether thermal energy is added or released. Okay, so let's see here. Thermal energy is the heat. Okay, so let's see here. Condensation is when a gas, here, oh, my bad. Here it's when a gas changes into a liquid. So gas to liquid, let me just see how the boxes come. Yeah, like this. So condensation, gas to liquid, here. And if you remember, in the previous question when we wrote them in blue, it means it's cooling down. So I'm just going to write R for released. Why? Because when thermal energy is released, it cools. And when thermal energy is added or absorbed, it heats. Okay? So here, gas to liquid, and the thermal energy is being released. Now, deposition. First, let's remember sublimation. Sublimation, S for solid, skips liquid, gas. So deposition, what's the opposite? Gas to solid. Gas to solid. So for something to change from a gas to solid, now guys, gas to liquid already needs like a really low temperature. So imagine gas to solid, this needs a really, really low temperature. So obviously, thermal energy is being released. Oh. Now evaporation. Evaporation is when it changes from a liquid to a gas, right? Liquid to gas. And what do you expect for something to evaporate? It's going to heat up. So thermal energy is added. Melting, solid to liquid. Yani solid ice to liquid water, let's say. What do you expect? It's going to become like water to freeze, right? So, here. So, condensation, gas to liquid. Here, you can scroll down to see. Deposition, gas to solid. Evaporation, liquid to gas. And melting is, where is it? Solid to liquid. And here, released, added. Okay? So melting, yeah, we're good. Let's go next. Here, the graph below shows the phase change diagram of a certain substance that was heated at a constant rate for a few hours. Drag and drop the terms in the box below to their correct change of state to complete the diagram. Now here, this is actually really easy. I don't know why they make the table look so hard, honestly. It's just to confuse you guys. Here, solid, arrow to liquid, solid to liquid, it's melting. Right? And here, there's just another arrow. Here they mean to put solid. So here, liquid to solid, it's going to freeze. So freezing. Okay? Now here, the liquid, they just mean to put it down here, liquid. So liquid, and here gas, they just want it here. So liquid to gas. So from liquid to gas, it's going to evaporate or boil. Just let me see the above. Here they want evaporation, but first, solid to liquid, we said, melt, and liquid to solid, freezes. And here, liquid to gas, look at the arrow here, same way, it's evaporating or boiling. Here they want evaporation. And gas to liquid, condensation. And here also, you notice here, the temperature and the heat. Okay? So here is just the change in state between a solid, a liquid, and a gas. Let's move through them now. A student wants to study how acetone changes state. He places a beaker of acetone on a hot plate and records the temperature in the table below the boiling point. Now guys, what did we say? The boiling point, look towards the end and see it should repeat 2 or more times. Okay, so let's see. 20, 25, 32, 39, 46, 51, 56, 56, and 56. 12 minutes, 14 minutes, 16 minutes. So this is a whole entire 2 minutes, right? And look what happens here. It's still 56. So what do you think the boiling point is? 56 degrees. Why? Because 56 degrees Celsius repeated 3 times. So basically 2 or more times. Okay? So what's the boiling point? 56 degrees. So just look towards the end and see what repeats a lot. Here, what are 3 results of boiling on the particles of acetone? So here, this is actually really easy. What happens to the particles? Remember we discussed, I'm not going to rewrite it again. Or actually, it's fine, I will. Here. So when something heats, right? So boiling heats, the particles, they gain energy. Why do they gain energy? How do they gain energy? Because they move faster. And let's just see the other ones. They gain energy. Yes, because the particles, they move faster. They lose heat? No, because it's boiling. Motionless, we said. No particle is motionless. Nope. They move freely in all directions. Now, guys, when a liquid changes to a gas. What are properties of gases? We said the particles, they move freely in all directions. I'm just going to write move freely for now. In all directions here. So here, obviously, when they turn into gas particles, they will move freely in all directions, and they leave from the body of the liquid. Let's say here you have the liquid, let's say in a pot. When it evaporates, what do you expect? The liquid is gonna leave the body of the liquid until it becomes only gas, right? So obviously, what happened to the liquid? The particles, they left from the liquid. So what are the three correct answers here? The particles gain energy, so they move freely in all directions, and they leave the body of the liquid, okay? Let's see. Underline a process from which matter changes to a liquid. Okay. We're just gonna write here liquid, something to liquid, and something to liquid. Okay? Matter, what did we say matter? Solid, liquid, gas. So solid, liquid, gas. Gas here. Okay? So let's see. Evaporation is from a liquid to gas. But what did it change into here? It changed into a gas. But what did we want it to change into? Change to a liquid. So evaporation, unfortunately, no, you're wrong. Let's see here, condensation. Condensation is when a gas changes into a liquid. Here, changes to a liquid, and here it changed to a liquid. So is condensation correct? Yes. Melting, solid to a liquid, right? And what does it change into? Liquid, liquid. Also correct. Boiling, same states as evaporation, so wrong. And freezing is when liquid changes to a solid. Okay? So here it changed into a solid, right? Here we wanted to change to liquid, not solid, so freezing is also wrong. And boiling, here it's also wrong. So what are the two correct answers? Condensation and melting. Also, what can you do? Just write the other two states, fill in the blanks. Solid and gas. Right? Can liquid change to liquid? No. So here, and then just check which change. So solid to liquid is melting, and gas to liquid is condensation. We're almost there. Okay. The bathroom mirror. Actually, no, let's just start with the easier ones, guys. Ice is left on the counter. Guys, obviously, when you're gonna leave ice on the counter, what do you expect to happen to the ice cube? Eventually, it's going to melt into liquid water. So, when you leave something outside for a long time, it's going to melt. Water left in a freezer, if something is left in a freezer, what's gonna happen? It's going to freeze. Here, a pond gets shallower. Here we have a pond, let's say. This is a pond. Okay? It was a really hot summer. Okay? And now let's say the pond, it shrunk. It got shallower. What do you think happened to the liquid? It must have evaporated, right? Because of how hot it was. So, when a pond gets shallower after a hot summer, also, what's a pond? It's a liquid. And after a hot summer, so what do you think? If something is hot and then you have a liquid, what is it going to change into? A gas, right? You lost some liquid. So, liquid to gas, what is it? Evaporation. Here. Frost forms. Actually, let's do this one. The bathroom mirror. Now, this one, it's a bit tricky, but we're going to think about it. Here we have the bathroom mirror. And then let's say here you were showering and the door is closed. Obviously, the room is gonna be really hot, right? So here, this is like, let's say, the hot particles inside the room. And the mirror here is a cold mirror. Cold mirror. So what do you expect is gonna happen when the hot particles touch the cold mirror? They're gonna change into liquid particles, right? And so many of these liquid particles, what is it gonna form? It's gonna form the fog, right? So something hot, so hot gas particles, because it changed into a liquid. When did it change into a liquid? When it touched a cold surface. Okay? So, when hot gas particles change into a liquid, so gas to liquid is condensation. So this one is condensation. Now guys, here the other two are a bit harder, but let's do this one. Solid carbon dioxide placed under normal conditions. Now guys, what is carbon dioxide? Carbon dioxide, I'm just gonna write CO2 actually here. Carbon dioxide is a gas, right? But here you have solid carbon dioxide. So solid changes into a, so here it's placed under normal conditions. So when carbon dioxide it's back to its normal conditions, it's gonna change back into the gas we all know, right? Either when you see solid carbon dioxide, خلاص, it's sublimation. Here, either way, just for more explanation, the solid carbon dioxide is placed under normal conditions, which is the gas, sublimation. Solid, skip, liquid, and then turns into a gas, that is sublimation. So here, solid carbon dioxide. And deposition, frost. Now guys, you live, let's say that in very cold countries, and let's say this is your window here. It's really cold on the outside. Here are the gas particles, okay? But then directly, it touched the even colder window. So what do you think is gonna happen? It changed into ice or frost, we're gonna say. So it was gas particles outside. So gas particles, it touched the cold, extremely cold window. And then what's frost, guys? Frost is a solid. So gas to solid without forming a liquid in between is deposition. So here. Indicate whether it's evaporation or boiling. Now guys, here it's important. So it takes place when the particles leave the surface. That should be evaporation. Large group is boiling. Okay, now I'm going to explain it to you guys. What is the difference if we had a pot filled with really hot water? It's boiling water. And we have a pond that's filled with boiling water. Basically here, if you're if you're boiling something, right, under the fire, let's say, right, if you want something to boil faster, suddenly all of these particles are gonna turn into a gas, right? For example, if you're cooking something, here a large group of particles suddenly change, it's boiling. Why? Because when you want to cook something, let's say, are you gonna wait for it to evaporate? No. This is why boiling, it's faster than evaporation. Evaporation. Right? Obviously, like if you're cooking, okay, and then you want the water to evaporate, are you gonna wait for days and days until finally evaporates? No, you're gonna heat it up under a fire here until suddenly here, when you see this word, suddenly change, know that it's boiling. Here, next, occurs at a specific temperature. Once again, how do I think about it? Boiling points. And what's the point of something? A point is a specific, like temperature, let's say in this case. Okay? So, here, boiling point, it occurs at a specific temperature. So, specific temperature. Unlike evaporation, guys, evaporation can happen at any temperature depending on the surrounding areas. Now here, let's see, takes place when the liquids on the surface of a liquid leave. So here it's not suddenly, it goes bit by bit. This is why this would be the progression of a pond, let's say after a few months. Let's say this is like after a year, and so on, keeps getting shallower, right? Until it turns into a little puddle. What is happening in the meantime? Evaporation. So guys, obviously, you're not gonna wait for that for like that much time if you're boiling something, okay? So, brief summary, they leave the surface of a liquid. So, slowly, evaporation, suddenly change. Particles suddenly change, boiling, specific temperature, boiling point. Next, which of the following is a physical change? Now, guys, remember I told you they're going to ask you this question. Physical changes can be changes in states of matter. Now, guys, what are examples of states of changes in states? We have melting, we have boiling, right? Let's say deposition, also deposition, and sublimation, right? So these are all physical changes. Okay? Let's see, guys. What is combustion? Combustion is the burning. When you burn something, it's going to produce ash, carbon dioxide, all of this. All of these are new substances. But a physical change needs no new substances, right? Substances. Right? Combustion of wood, it forms ashes. Directly new material, wrong. The reaction, interaction, flammability, all of these, whatever, like reaction or interaction, chemical change. But what are we looking for here? Here we're looking for a physical change. So do we need this? No. Sublimation, it's a change in state, right? Change in state. And what are changes in states? Oh, here, state. These are physical changes. So a physical change is a change in state. And look here, I also wrote it, sublimation. Okay? So sublimation of a solid, which is a change of state, is the physical change. Okay? Guys, please don't get confused. Like, don't say sublimation, it forms a new material. It just changes what it's made of, right? For example, when solid carbon dioxide, sorry guys, I'm gonna go back. Solid carbon dioxide, it's gonna turn into carbon dioxide. But here, let's say here we have solid carbon dioxide, and here we have gas carbon dioxide. But what do they have in common? You still say carbon dioxide. You don't say solid carbon dioxide, gas, water, right? You're not gonna say that. Now let's move on. What can help store large quantities of gas in containers? Gas liquefaction, guys. Remember when I said here you're gonna store the gas particles inside cylinders, remember? We're gonna be increasing the pressure, favoring the attraction, until what? It forms liquids, right? So what can help store large quantities of gas in containers? Gas liquefaction or liquefaction. Okay? Also, guys, I remember I saw this in the grid before. It's like it asked you, why is gas liquefaction. I'm just gonna write like this, like convenient. Okay, I remember it asked something like that, and the answer was, it was because it helped stores large quantities of gas. Okay, like you're taking so much gas at once and then you're changing it into a liquid. It's faster than condensation, right? So this one, when you see store large quantities of gas in containers, what's this? Gas liquefaction or gas liquefaction. And finally, the last question, what happens to the boiling point of a substance when the pressure increases? Now, guys, here you just need to know this. The boiling point increases when the pressure increases, and the boiling point decreases when the pressure decreases. Okay, this is why, guys, for example, when you're cooking something in a pot, it's gonna be better to close it, because here you're adding pressure, and eventually, let's say the water inside, it's gonna evaporate faster, or boil faster, sorry. Okay, so what happens to the boiling point? So when the pressure increases, the boiling point also increases. So they move in the same way, you can say. Let's submit. Okay, so this is it for section 2.3, and thank you so much for staying. And good luck and best of luck for your science finals.